right, sorry, being a little slow this morning. So a couple of announcements. I kind of mentioned it last Thursday, but now I'll make a more formal announcement. So, can't spell. So on June 3rd, I had mentioned that I'm doing some outreach event, and it's going to be in Grants Pass, so at Grants Pass High School. And so I was just wondering if anybody wanted to come join me. It would just be, volunteer thing. We could put it on your resume, did some outreach. It's for elementary school kids. And I think we're like setting up there around 9:45. And I'd have to double check my email, but I think it goes until 2 p.m. if I remember correctly. So if you're interested in helping me, even if you're like not 100% sure you can make it, let me know like today, because apparently there's some background BS forms and some like COVID BS forms to fill out. So we have to do that like ASAP. But like I said, I'm looking for maybe a few volunteers. And if it entices you, I'm thinking about doing the liquid nitrogen ice cream and maybe some flame tests. But that all depends on bodies and hands that I have to help me. So if you're interested, just let me know. You can talk to me in lab about it, and I can get you the forms so you could fill them out during lab, and I can send them to whoever they need to go to. And so also just putting this on your radar. So next week, I think that's May 31st, there's going to be the end of the year barbecue. So I don't know if you've seen announcements on that in your like student stuff, but I have volunteered to be a victim of the dunk tank. So you can dunk me and take out all your chemistry frustrations out at the end of the year there. So there'll be food as well. I think that's from like 11 a.m. to 1 or 2. I think it's 11. Maybe it's to 2 actually. So I think it's 11 to 2, and so if you're on campus or come to campus for some free food and getting out your anger on chemistry. All right, any questions about stuff as we barrel towards the end of the year? I have the lab set out. I think I forgot to get out the homework or it's somewhere. And then people asked about like rubrics for the paper, so I'll print those out. I think for lab, I forgot to bring them with me. Hopefully my chat's functioning. It looks funny on my end. If you're there, say hello. I'm not sure I can see the messages or not. Questions?
So I'm looking at the homework from last week, and one of the sections is to identify each of the following reactions as radioactive decay, nuclear transmutation, fission, and fusion. Did we talk about nuclear transmutation, fission, and fusion in class?
I did not mention those terms.
Okay.
I also have a question about that spot. It said that protons decay into neutrons, but you can't decay into a hadron that is heavier than you, or at least you shouldn't be able to. Did we touch on that?
So that sounds like electron capture. So if we go back.
No, not electron capture. You said negative beta radiation, or positive beta radiation, I can't remember. Which could be two things. It could be a neutron decaying into an antiproton, or it could be a proton turning into a neutron. And I looked it up, and it said it was protons that are decaying into neutrons, which I didn't understand.
Sorry, so your question, there's two different types of beta decay, but if you look it up, people will tell you different things depending on how they find beta decay, positive beta decay, positron decay. So there's all these different names for the same thing. So beta decay is a neutron, so it starts as a neutron, at least beta decay negative, and then you make a proton and then the anti-electron.
Then I would be talking about beta decay positive then.
And so then positron emission, you take the proton, and then you get the neutron plus that positron, which is a massless electron, basically.
Yes, but neutrons are heavier than protons, so.
No, they have the same mass.
It differs by a very small amount. We just ignore it because it's the weight of an electron, but it's still there. And like, can a proton just shoot out positrons and then electrons from the neutron and then just keep going back and forth and generate infinite protons and electrons? That doesn't seem to make sense. You know what I mean? Because like if a neutron turns into a proton and releases an electron, and a proton turns into a positron or turns into a neutron and releases a positron, positrons and electrons are the normal matter and the antimatter equivalent of the same thing, and they obliterate each other and produce energy. So can you just go from proton to neutron to proton and constantly swap back and forth producing infinite positrons and electrons? Because that doesn't make any sense.
No, because I mean, it has to go through a certain decay pattern. You can't just decay stuff, but maybe we should talk later. And then, Nikki, what was your question again?
So about fission, fusion, and transmutation.
Okay.
It's also not in the chapter, the inter-chapter.
All right, so let me pull up the homework, sorry, and then maybe we should go over that. Because I don't want...
Maybe a proton absorbs ambient energy.
All right, so then... Oh, are you talking about 4 here?
Yeah. I mean, the two radioactive equations are kind of obvious, but I don't know about the, yeah, we don't have any information on the transmutation fusion.
Okay. All right, so let's try to define all those then. So radioactive decay, so that process, or at least what it's kind of more referring to here, is when you start with kind of one reactant and then it decays. And of course, right, you'll make your daughter plus whatever radioactive species. And so that's different from nuclear transmutation in that that would be like kind of two things coming together. So nuclear transmutation. And we didn't look at too many examples, but for instance, like this second one is an example of nuclear transmutation where you have an alpha particle acting as your reactant, and then it's adding to another appropriate isotope, so it goes down the decay pattern. So I'll kind of put like 2 reagents. And then fission, see, my only question is like, You know, maybe you could classify other things as fission. But so fission is where you have, right, splitting of nuclei. But you could argue with me that like radioactive decay and fission are kind of related. And, you know, you could argue that they're the same. I think the homework was trying to make the distinction that if you got like two different products, so if you started with like a heavier isotope and then made two different isotopes, that's more fission. But I mean, I would still call it radioactive decay because it's still like a type of radioactive decay pattern, and you're making like your neutron particles. So there's some like kind of wiggle room there with the definition. And then fusion. So fusion is what the sun does. And so actually, there was really recent research that I think made fusion. Did we talk about that in this class? I think we like mentioned it. But it's combining lighter isotopes or nuclides to make heavier ones. So that's right what the sun does. So it starts with hydrogen and helium and starts making heavier and heavier elements until it reaches iron. And so again, fusion we don't typically see on Earth, but like I said, there was just recent research where they like pointed a bunch of lasers at this little ball of gas. So it was crazy conditions, but they had like a little ball of hydrogen gas and then like put a bunch of lasers all concentrated and multiplied towards it, and they achieved fusion and actually got more energy out than they put in, which was a huge accomplishment, and that's what fusion does, but whether that's actually feasible is up for debate.
They got more energy out in terms of 100% lasers. They were using 42% efficiency lasers, so unfortunately it can't make an engine yet.
Yeah, so that's why. A long way to go, but basically that would be this last one where it's telling you there's 4 equivalents of hydrogen, and then it made something heavier, so in this case, helium-4.
So in the one that you have labeled C, like fusion and also radioactivity, radioactive, what is the 3N? What is that?
Neutrons.
Oh.
Yeah. And so this one, I think, actually you could call this not A, but rather nuclear transmutation, because you have that neutron kicking off the decay. So that's how it works in a nuclear reactor, is you have the neutron, hits uranium-235, and then starts the chain reaction. But there are also like other radioactive patterns where like uranium goes to thorium instead. So it kind of depends on how they're initiating it and what like species they're using.
They're using tritium in fusion.
So did that help with that?
Kind of. Are we responsible for knowing those types of equations?
I don't think I'm going to ask anything too nitpicky like that, like the definitions like that. I care more that, let's say I give you, you know, alpha plus beryllium-9 gives you a neutron, and then you'd have to identify like carbon-12. Like that's what I care more about, is that you can balance the nuclear reactions.
Got it.
Oh, come
How
on.
do we know that it gives us a neutron?
Oh, like I would have to tell you. So you'd have to be.
Okay.
Or, you know, the other way, it decays to carbon-12, and then you have to figure out that there's a neutron. And I'm trying to glance at. Yeah, or the other thing that you'd be asked to do on the exam is, you know, the radioactive decay questions.
Which seem more straightforward than
Fission fusion.
Yeah, so just like using either that equation, or we didn't go through the simple method, but we'll kind of cheat. We'll do an example. Oh, man. So the one thing we didn't quite go over, just because I felt like we'd already seen it before, but let's do an example. So how long does it take for a 36 milligram sample of radioactive isotope with a half-life of 2.25 days to decay to 9 milligrams. And so there's two ways to do this problem. I'll give you all a few minutes to think about it.
5 days, no.
But you can do kind of the pure math method, or try to set up like the half-life way. Like how many days and how much sample are after like 0 half-lives, 1 half-life, 2, 3, 4. And that's kind of an easy way to approach this type.
If we're going to be doing this on an exam, is it going to be like nicely, neatly divisible like that? Or are you going to give us something like, how long does it take 40 grams to decay into 16? And then we would have to like make a distribution and figure out the ratios. Like, because right now, 2 half-lives just gets you there, and it's all nice and neat. But if it didn't nice and neatly go from 36 to 9, what do we do to solve that?
Then you would turn to the equations.
I have a question, by the way. So, with radiocarbon dating, the half-life on carbon-14 is relatively small. Relatively small, as in it's not like a billion years. But our planet's like multiple billion years old. How is there any of that really left on our planet? Carbon-14.
That's not how it works. You compare it to what you expect the current ratios to be based upon like the natural abundance, and then you compare that to the ratio of the products because they stop making and integrating carbon into the lifespan.
Yeah, okay. But how do we have any carbon-14 to begin with? Like, shouldn't it be an insanely small, almost imperceptible amount with what the half-life is versus how long our planet's been around?
But more is made, so it exists naturally, but let's focus. All right, so what do we get for this answer? So we could talk after class, because that's off topic. So how do we get that?
So I took 36 and halved it for one half-life. Then I took 18 and halved it again for the second half-life. And then I multiplied the half-life by 2.
So 5.5 days or something?
Oh, yeah.
Yeah, so that looks good. So that's like the easy way to do it.
That's
And-
incorrect. It's 4.5.
Oh, 4.5, sorry. So 4.5 days. And so hint, hint, you'll have a similar question like this on your quiz, and you can just use the easy method like that. Otherwise, right, we have to use our T half-life equation, find our K first, and then plug that all in based off of what we want. So write the ratio of our original amount to amount at T. And we've done this before in the past, which is why I didn't want to belabor it. But if people wanted to go over it, we certainly can.
Can we go over the same example using that information?
Yeah, so then, now we have to try it out. So we have to use this equation. So T half-life is equal to 0.693 over K. So we have to solve for K. But we have our T half-life. So 2.25 days. Oops. So then if we divide, that gives us 1 over K. And just keeping, we're in days units. And so then to plug it in, we use this equation. So natural log of whatever amount at time we're interested in over original equals negative KT. And so in our case, original is 36, 9 is our T. Sorry, I'll just simplify that. And so let's plug that in. And so we get the same T that we got by kind of our easy method, which is the 4.5 days again. So I'll say for today's quiz, I'm expecting people to use the easy method. Feel free to, of course, knock yourself out with this method. And on the exam, I can't say for certain, I would have to look at the numbers, but you might need these equations for the final exam. So that was brought up as a concern. So questions, we feel okay about the math on this? any other questions on the previous chapter, since you'll have your quiz on that? And I didn't ask like other definitions, because I know your homework does like REM and RAD and other stuff, but we just didn't talk about that.
Is today's quiz on O, F, G, and H?
Yeah, so there'll be like a little bit of alkane naming, but I try to keep it hopefully more general. All right, so let's go back to our transition metal chapter. And so we were looking at these ligand substitution reactions, and I was trying to find a cool demo, but I didn't quite nail it down yet of what to use, since a lot of these compounds can be kind of toxic. So for example, right, you can make the nickel hexaaqua compound, that's fine, that's nice and green. Nickel 2+, that's pretty standard for nickel. Then if you add it with ammonia, so again, this is going to be your L-type ligand donating 2 electrons to nickel, just like water, so they can do this ligand substitution reaction, and all the ammonia then replaces the water, and you get this blue-violet color. And of course, water is colorless. And then from there, you could add cyanide to it, and this is what I didn't want to deal with. So unfortunately, like potassium cyanide or any sort of cyanide salt is toxic, and didn't really want to create a bunch of toxic waste, at least not here. But what you can do,
Let's create toxic waste somewhere else.
yeah, I just didn't want to create disposal. I'll figure out something else later. And so then if you do ligand substitution, what's interesting about this as well is you only get 4 on there. And then there's questions of whether this would be square planar or tetrahedral, so you'd have to look into more information for that. So that's not obvious from this, but that would be kind of an orange-yellow color, and that could, of course, tell you something about the geometry as well. All right, let's go into naming, and we'll go into the fun stuff. And so to name them, and this is just kind of a loose rule with more of these like simple ones. If you go into research, right, people come up with all sorts of names and shortcuts for their ligands and different naming schemes. And so coordination compounds often contain a complex ion, and that just means it's ligands attached to a metal. And then there could be some sort of counter ion, so we mentioned that would be just an outer sphere ion to help balance that charge. So, you know, that depends on the oxidation state of your metal, of course, what that counter ion could be. So it could be positive, right? We mentioned that you could have some outer sphere positive cations, or like what's also used is like BF4 if you have like a positive ligand. That's the more common one. Or any sort of other like boron, tetrafluorate salt, triflate. And so if there's a cation and an anion, the cation is named first. And so in this first one, so there's no cation, right, ion here, so no like sodium, potassium balancing it out. But it does seem to have these chlorides, so it does have counter ions. And then this would all be inner sphere complex to it. And so you can just start with the ligands, so it has 6, they're all the same, and we used our same prefixes, so hexa, then aqua nickel, we indicate our oxidation state. So of course, water's all neutral. The charge is coming from our chlorine, so chlorine H -2, so nickel's +2. And then just name the cation or anion like we've done before, so chloride. And so ligands are also typically listed in front of the metal. And so in this case, we again name our ligand, so hexaamine. And I'm pretty generous with the spelling since I don't know why it has a double M now, but different rules for spelling. But again, it's copper 2 with our bromide.
And a double A, that's funny.
Yeah, and there's all different rules for drop the vowel, keep the vowel, so I'm not too picky on your spelling, just as long as you get pretty close and I can decipher what it is. So our hexaamine, copper 2 bromide. And so then if we have a case of 2 different ligands are on the complex, you list them alphabetically. And so breaking it down, right, this is outer sphere, so our counter ion. And so we'll start with just what's attached to your ligand. And so looking at oxidation state, so chloride is -1, each of these nitrates, -1, so that gives us cobalt 3. And now we have, right, penta, aqua versus just chloro. And so aqua is first. Remember, you don't use the prefixes when naming alphabetically, just like we did with OChem. So similar concepts, and then it's penta aqua, chloro. And if it's 1, right, you don't have to say mono. But it's penta aqua, chloro, cobalt 3, nitrate. And so again, you have your di, tri, tetra, penta, hexa prefixes. And so you could also have, they may already contain prefixes denoting a number, such as ethylene diamine. And so the di means that there are 2 amino groups in the ligand. And so if you were to draw out ethylene diamine, so this is a pretty common ligand, but with this diamine, and you can tell it in the formula, but if you didn't have this formula here, it says ethylene, so that's 2 carbons, so start there. Ethylene, so double bond, and then diamine is 2 amine groups, and so it looks something like that, and that's what we have there for our formula. And so other things, so this is a really common ligand actually, and common starting material. And so you can break this down. So you have tetrakis, triphenylphosphine, palladium, 0. And this is, again, a nice palladium 0 source. And so you can break that down on what it's saying. So start with triphenylphosphine. What is that? So triphenylphosphine looks like this. So triphenyl, so 3 phenyl groups, phosphine. And then that's going to be coordinated to palladium. And then the tetrakis is telling you that it's ×4 for this whole thing. So this is a monster ligand. And it will be better if we just look at it. Oh, that was not a good picture. There we go, I wanted this picture. So you could just tell how bulky it is. So palladium, and since it has 4 of them, in this case it took the tetrahedral configuration, and then you can just appreciate how bulky those 3 phenyl arms are on each phosphine. And it's nice and pretty. It's like this yellow crystal powder. Fairly expensive though.
What is it typically used for?
Just a palladium 0 starting reagent. Like actually I used it a lot in my research just because if I wanted to put palladium on there, it's easier to start with like a metal 0 source and then it can undergo oxidative addition into your compound basically. But if you look at it, so like 1 gram is $42, so that's pretty pricey. You know, you can get bulk deals, but it's pricey. So that's why, you know, people like using it. You just heard that I used it, but if we're trying to do research, you know, it'd be much nicer to get the nickel version, but we've kind of touched on the issues with nickel versus these workhorses. And so just more ligands for you. So same ones we've kind of seen before, right? Fluoro, chloro, bromo, iodo, those can still be ligands. Cyano, hydroxo, nitro. Again, those are ligands. And these are all with a -1 charge. So we see that a lot. Carbonato, not as much. Oxo, yes. And then our neutral ligands. So these are your 2 electron donors. You have amine, aqua, carbonyl, and nitrosyl. And so here's just more examples of those chelating or polydentate ligands, however you want to refer to them, or they have different names, again, just who's writing the paper. And so in this case, you have your oxygen, so it can donate 2 electrons there. So this is an oxalate ion. There's the ethylene diamine ligand. And so, right, bidentate, we kind of went over that before. That just means a ligand that has 2 points where it's binding to. So this is a fairly common structure. Sometimes they use the phenyl backbone as opposed to that cyclohexane, but similar sort of design. Sometimes phosphorus can also act as your bidentate. So all sorts of structures, whether you want to use more amine base or swap them out for phosphorus. You could also swap this out for sulfur, but sulfur is more difficult to work with. It's just softer, so it binds poorly. And then you have your tridentate, and this can go on and on and on. So this is a crown ether structure. This is going to be a simple one, but then you can put some sort of metal in the center, and so all those oxygens bind to it. And I'll just show that you can kind of go crazy with these crown ether complexes, so you can have 4, 5, 6, and kind of go on and on with different crown ethers depending on what you want to do. All right, let's look at these isomers. And so we have different isomers. So if we look, let's start with the planar structure here. So this is for square planar geometry. And so you have 2 different potentials here. So if you have different ligands on there, if you have the same ones next to each other, so that they're right next to each other, kind of this 90-degree angle. So that would be considered cis, where they're like on the same side. And so you're looking right at the relationship of the two ammonia and the two chlorines, so they're both cis to each other, versus the trans isomer of this complex, where now the chlorines and the amines are across from each other, and so now that's considered the trans isomer. And so they might have different colors or ways that you can distinguish them, or crystal structures. And then for octahedral complexes, you have the cis relationship, again, if they're right next to each other, so it could be chlorine-chlorine, or, right, just think about reorienting the molecule, and just as long as they're next to each other. So if the chlorine instead was going up and down, and then the other chlorine still in the middle, that's still the cis isomer. Draw that better. So chlorine. So that's still cis, right? Same compound. And then trans isomer, now the chlorines are across from one another. So along the z-axis, so of course you could swap them here. That would be the same thing rotationally if they were there and there, or there and there. So either way, you can rotate it, and it would be trans. And so in this case, it shows you that you can identify them by their difference in color